I had started talking about magnetism and had gotten to the point where I said that if you shoot a charged particle through a magnetic field, such as an electron beam in a vacuum tube, or it could be some ions in a mass spectrometer, or it could be some ions in the sun, or there's lots of settings where this kind of thing can come up. If you have, and actually it can be inside of a wire too. We'll get to that in a little while. It doesn't have to be an empty space. But if you have a moving charge in a magnetic field, the force on it is QVB sine of theta. Well, figuring out how big the force is, that's just dropping numbers into a formula, which is like, this is probably the 10,000th formula I've given you to drop numbers in. That's not the most challenging part. The tricky thing is the direction of the force. The force is perpendicular to both the direction of the magnetic field, which is the direction that a compass would point, and it's also perpendicular to the direction of the velocity vector. In other words, the direction the charge is moving in. So the last thing I had you do was problem number 1, where you had to figure out the magnitude and direction of the force on an electron. Like I said, the hard part, I think, the novel part, at least, is figuring out the direction. So in example number 2, you get some more practice finding the direction. We aren't going to bother with any numbers because I think once was enough for that. So I'll give you a little time and then go through part A. In case you're completely stuck, that might unstuck you for the rest of it. And then I'll give you some more time and then go through some more of it and so on. Yeah, maybe before I paused it, I should have reminded you how the right-hand rule works also. It's been a week after all. Let's just make up an example here. If you have, let's say, a magnetic field that points out of the page like this. So that's the B field. And let's say, I'll make it different from any of those. Let's say you've got an electron, and it's going to the left like that. So a magnetic compass would point this way, and the electron is going that way. You get your right hand, and your fingers point in the direction of the field lines, which in this case would be out of the page. And your thumb points in the direction of the velocity vector, which should be to the left. Your palm pushes on the electron. I should have drawn it a little lower down. My arm doesn't quite bend that way. But your palm pushes on the particle in the direction of the force on a positive charge. So if that had a plus sign on it, the magnetic force would be pushing it upward, which means that as the particle went along, it would kind of curve like that. But it's not. It's a negative particle that reverses it. So as the next few moments pass, the electron is going to kind of curve downward like that. Okay? So that's what you need to do in each of these situations. I think I'll go over maybe the first two, A and B, and then go around the room one more time before I do the rest of them. So in part A, all those X's mean field lines that are pointing through the page away from you. Your fingers are the field lines, so they point that way. Your thumb is the velocity vector, so it points to the left. Your palm would push downward on that particle if it was positive, but the minus sign on it, you know, kind of as a clue, it might be negative. So that reverses the direction. And the answer for part A, let's see, where am I on the screen? There. For part A, the answer is plus y. As a number of you had. For part B, there is no force on that particle. Because, let's go back to the formula. Force is QVB sine of theta. Theta is the angle between the direction of the field and the direction that the charge is moving. Well, those two things make a 180-degree angle in this case. The field points toward the top of the page, the velocity points toward the bottom of the page. You stick those two arrows together, it's 180 degrees. Sine of 180 degrees is 0. Or if you don't want to get too tangled up in formulas, just the general idea is that the force is a maximum when the particle cuts across the field lines. If you go along the field lines, there is no force, no matter how strong the field is or anything else. So, none, because sine of 180 degrees equals 0. Okay, a few more moments for the rest of it. The rest of them. Part C. The electron is moving out of the page toward you, so that's the velocity vector that's perpendicular to the page this time. Your fingers point in the direction of the field lines. Your thumb points in the direction the particle is moving. So I get my hand like that, and my palm would push the particle upward if it was positive. But once again, I made it a negative charge, and so that reverses things. The answer is negative y. The electron, or whatever it is being pushed toward the bottom. Down here is where I identified which way is which, you know, different books do it different ways, but we're saying the XY plane is the plane of the page, and the Z-axis is perpendicular to it. So with that kind of setup, it's the negative y direction. That's the answer to part C. Indeed. This time it's the field lines that are sticking out of the page. So once again, field lines are the fingers. Your thumb points in the direction of the velocity. And once you get your hand oriented that way, your palm pushes on the thing toward the left. This time it actually is a positive particle, so negative x direction. And in E, did you figure this one out? I didn't look at anybody's paper on this one. Yeah, exactly. None, because V equals 0. Force is QVB sine of theta. In part B, it was the sine of theta that made it 0. Here, the thing isn't moving, and magnetic forces, they don't have much in common with air drag, or viscous drag in general, but that's one thing they have in common, is they're both velocity-dependent forces. If you drop Well, if a skydiver jumps out of an airplane, the faster he moves, the greater the air drag on him or her. And magnetism is the same as that in that one way anyhow. The faster something moves, the bigger the magnetic force on it is. So, like it says in parentheses, there are some applications to electric charges in empty space moving through a magnetic field. Vacuum tubes, while to a large extent an obsolete technology, have not completely disappeared. They're still, well, for example, most people have a microwave in their house, and the microwaves come out of a vacuum tube called a magnetron. There are, as I understand it, still some musicians out there who are just hardcore vacuum tube people that say, you know, that transistorized stuff just doesn't sound the same. And so, you know, you still find them here and there. Aside from that, well, if you get into physics research, for example, the Large Hadron Collider and other large particle accelerators like they have down here on Long Island or in Illinois, or the Linear Accelerator out in California, these things are basically just enormous vacuum tubes that are just miles in size. But mass spectrometer uses a beam of ions in a magnetic field in empty space. That's a fairly common piece of equipment in a chemistry lab used for identifying unknown substances. But maybe the most important and common applications of all of this force I've been talking about don't involve particles in empty space. Rather, you see, magnetic fields will penetrate a wire almost as if it wasn't there, okay? Unlike electric fields, which have some issues with metal, but magnetic fields just go right through it. So at least a DC field does. So if you have an electric current in a wire, that electric current, well, it's just a bunch of charges moving through the wire, right? And those moving charges feel this same force just as if they were in empty space. The only thing is, the charges can't leave the wire. So if the moving electrons in the wire get pushed to the side, they take the rest of the wire with it. So there is a force on a current carrying wire. And well, you could calculate it from QVB sine theta, but it's kind of inconvenient to have to come up with numbers for the charge on little things that you can't even see and figure out what their velocity is. Much nicer to have numbers that you can get from some $20 meter and a 95-cent ruler. So I'm not going to write out the step-by-step derivation, but if you just make a few substitutions into the equation on the previous page, a couple lines of algebra, you can show from QVB sine theta that the force on a wire of length L, like it shows in the picture, is ILB sine theta. The sine theta and the B just get carried over, and the Q and the V, where Q is the total moving charge in the wire, is equal to the I times L. So there's a force on a current carrying wire, and it's equal to that, and the direction is the same as we were just working on here with the, like in this picture here, the direction that the charges are moving is toward the right, and the direction of the magnetic field is kind of through the page away from you. Well, that's one way of taking the picture anyhow. If the magnetic field was through the page away from you, the wire would get pushed upward toward the top of the page. Same right-hand rule that you just used 5 times in that other example. Of course, the direction in which positive charge is moving is the direction of the electric current. So maybe when it's a wire, maybe it's more convenient to think of it that way. The direction that charge is moving, the direction of the current, whatever way you want to think of it, that's going to be your thumb, just like it was in all these other things. So, why is this force important? You may have heard of a little device called an electric motor. They are everywhere. There's one in that fan over there making the fan spin around. They turn the wheels on locomotives, and of course now electric cars are the up and coming thing. And there was one in the electric shaver I was using this morning after I got out of the shower. And you know, motors are everywhere. And yeah, it does kind of go sometimes when I first turn it on. Yeah, so a motor is basically a coil of wire. I think in one of the labs coming up, I've got a simple little demonstration type motor that you can look at. All it is a horseshoe magnet and a coil of wire mounted on a pivot. And you start sending electricity through it and it goes spinning around, because in that coil of wire, you've got current carrying wires in the magnetic field that comes from that horseshoe magnet. And the force pushing on the loops of wire in the coil pushes it around. It makes it turn, to leave out a few important details. And there are other devices that make use of this force also, but a motor, I'm pretty sure, is what most people would think of as the most important one. So, one more time, just to beat this completely to death, but it does seem to give people a little trouble, so some practice is a good idea. It's similar to the example that you were working on 10 minutes ago, except now instead of free charges moving through empty space, you have a current carrying wire in a magnetic field. So the question once again is the direction of the force. And we'll pause for a moment so you can think about that, I'd say. But part A says here on this piece of paper that the answer is minus Z. Let's see if I can. Fingers go in the direction. I should shift the camera over there again. Fingers in the direction of the field. Thumb in the direction that positive charge is moving, which is to say the direction of the current. Arrow with the I by it. Well, if my fingers are that way, and if my thumb is that way, then my palm is pushing that wire through the page away from me, which is to say the negative Z direction. And then over here in part B, well, now we've got just a little dot for the current. Hopefully everybody understood what I meant by that. That means you've got a wire here that's perpendicular to the page like that, and the dot is the current coming out toward you, okay? So thumb in the direction of the current, and your fingers pointing in the direction of the magnetic field. My palm is going to push this wire toward the left. And when it's in a wire like this, you don't have to worry about, oh, I got to reverse it because it's negative. The direction of the current, by definition, is the direction of positive charge flow. So it's always going to be the direction that your right hand pushes it, okay? Which is to the left here, negative X. And that's followed up by another question. So it's the same sort of thing again, except I threw some numbers in with it. So you not only have to figure out the direction of the force, but you also have to figure out how large it is, which, as you can see by the answer written underneath, is not very large. So the electric company doesn't really worry about this kind of thing very much. The forces from the wind blowing against the wire are a much more significant factor. Pause this. Number 5, or 5-4, actually. So the magnitude is just throwing numbers into a formula. ILB sine theta, where theta is the angle between the wire and the magnetic field. This wire has 50 amps in it. It's 65 meters long. Maybe that's the distance from one pole to the next. A Gauss is kind of a handy unit when you're talking about weak fields like the Earth's, but for purposes of calculations, you need Teslas. And if you don't happen to remember, you can look it up on the last page of your formula sheet. But there are 10,000 Gausses to the Tesla, so you have to move the decimal 4 places. So 0.000, that's 4 zeros and a 6. As for the angle theta, well, the question says that the current is flowing in the x direction, and the field points in the z direction. X is perpendicular to z. Theta is the angle between the field and the wire. So 90 degrees, sine of 90 is just equal to 1. So it's a pretty small force, primarily because it's a pretty weak field. A powerful motor would have significantly stronger magnetic field in it than a fraction of a Gauss. The direction. Well, we draw some sort of a picture here. If the blackboard is the XY plane. The z-axis is perpendicular to the blackboard. I'm going to try drawing in perspective, like the last art course I took was in 8th grade. But one of the topics he covered was perspective. And so this is supposed to be, so this is not supposed to be a line running through the first and third quadrants. This is supposed to be the z-axis. It's like you're looking into the first octant at an angle, you know, and it's, hopefully you get that. Anyhow, no, you don't. Well, my alternative is to stick a little blob of clay on there and some sort of a stick in it sticking out of the blackboard, but it's wait a, let me try again here. So now it's just got another box in it. So this is the idea, okay? Let's say that, I should do this on camera. Let's say that's the origin there in the corner of the box. What I'm trying to draw is like, see this is the x-axis and this is the y-axis. And this line here, that's the z-axis. And when you look at the way I'm holding the box on the computer screen anyhow, it looks a lot like what I sketched there, because you've got this z-axis kind of going along at an angle there. So that's what I was attempting to convey. Maybe I should have taken some art in 9th grade too. Anyhow, the question says the magnetic field is in the negative z direction. So that's that way. And it says the current, whether you want to think of it as I for current, or if you want to stick with the notation we were using at the beginning of this class, V for the velocity of the charges inside the wire. It's the same direction, however you want to think of it. Come along with your right hand. And you point your fingers in the direction of the field. That's through the blackboard away from you. And your thumb points in the direction of the current, which is to the right. So if you get your hand like that, your palm pushes upward on the wire. And so that's how you can get that the direction of the force is in the positive y direction. On the next page. Now, magnetic fields not only have an effect on moving electric charges, moving electric charges are also where magnetic fields come from in the first place. It's like any other kind of force. Gravitational forces come from masses. The Earth is more massive than the Moon, so it has a stronger gravitational field. And mass is what feels the effects of a gravitational field. A more massive object it weighs more than a less massive object does. With electric fields, charge is what produces the field. You find electric fields around charges, and charge is what feels the effects. You place a charge in an electric field and it gets pulled on. And it's the same way with magnetic fields. Magnetic fields come from electric currents, which is to say charge in motion. And charge in motion, electric current, is what feels its effects. I have a short demonstration to demonstrate here, but you need to be able to see which way this compass is pointing. So you're going to have to get out of your seats for a moment. And I'm going to have to hold this thing at some sort of an angle. So let's see. Can I get it so that the direction of the needle shows up in the picture? No. I don't know if the lights are too bright. Well, people at home will just have to take our word for it. Anyhow, I've got a power supply here. Current comes down this wire, goes in here. This vertical section is the part we're interested in. And then it goes on and completes the circuit back to the power supply. So at the moment, the compass is pointing north, okay? Toward the blackboard is north, because that's the Earth's field. Power supply is off. Notice when I throw the switch, well, those of you who are here can see that it started pointing the other way. This compass is now pointing that way when it's there. I'll put it over here. Now it's pointing that way. If I put it over here, now it's pointing that way. Really wish it'd be nice if there was some way to get that to show up on the video, but anyhow, pointing that way, even though you can't see it. Actually, yeah, when I put my finger right there, it blocks the light just right. You can see the needle. You put it here, and it points that way. Well, anyhow, it's pointing that way. And I might as well just give up and set this thing down. But the thing to notice is, well, first of all, notice that the compass was affected by having a current flowing in this wire. So clearly the wire is creating a magnetic field. Furthermore, notice that everywhere I put the compass, its direction is tangent to a circle around that wire. Okay? And let me pick this up one more time. Notice that it's right-handed. The current is flowing up the wire, right? This is positive, this is negative, so it goes that way up the wire. And this is sketched, well, it's described up there in the notes anyhow. I guess I didn't try and draw a picture of a right hand, but what you do with your right hand this time is you grab the wire with your thumb pointing in the direction of the current. The current's flowing up the wire, so if I was to wrap my fingers around there like that, okay, notice that my fingers wrap around the wire pointing in the direction of the magnetic field. My fingers, when they are there, point that way, just like the compass does. There, see, it points that way. Over here, it points that way, and so on. So that's what I wanted to show you. You can sit down. So up there on the top of page 19 is a sketch of what I was just trying to demonstrate here with this wire and magnetic compass. You've got, in this case, a current flowing through a wire toward the right. That electric current creates a magnetic field around itself, which I indicated with a few field lines. I think I may have mentioned last week, magnetic field lines never have a beginning or an end. That's a difference between electricity and magnetism. Magnetic fields are always loops. Electric field lines begin on positive charges, they terminate on negative charges. Magnetic field lines are always loops. Grab it with your right hand. Pretend this pencil is the wire. Grab it with your right hand, with your thumb pointing in the direction the current flows. My fingers wrap around it. You know, they go up the back and down the front, and that's which way the field lines go around. So that's the direction of the magnetic field. What about the strength of the magnetic field? Well, not too surprisingly, it drops off with distance. If you're closer to the wire, the field is stronger. If you're farther from the wire, the field is weaker. And the other factor that's involved is the current. If you have more amps in the wire, it makes a stronger field. So B equals mu 0I over 2 pi R. R is the distance from the center of the wire. I is how many amps. Mu is a fundamental constant called the permittivity of free space. And if you're working in SI units anyhow, it has a value. Mu 0, unlike some of our other fundamental constants, doesn't have to be measured. It is defined to be precisely 4 pi times 10 to the negative 7. So there's a couple of examples coming up where you'll use that, but let's see if I covered all of this, said that. Need to explain that. So I said a minute or two ago that where magnetic fields come from is electric currents. I need to explain permanent magnets. If you've got some magnet, you know, one of those little flat magnets from the fire department or whoever, stuck on your refrigerator at home, you don't have to plug it in, and it doesn't take batteries. So where are the electric currents? Well, for permanent magnets, you have to look at the atomic level. Any kind of an atom is full of moving electric charges, whether it's an iron atom or a sulfur atom or anything else. In some case, well, before I get too far ahead of myself, any of those moving charges amounts to a tiny electric current. If you have an electron orbiting around a nucleus, that is a little loop of electric current. Okay, charge in motion is what electric current is. It doesn't have to be inside a wire. Now, also there's the spin of the particles. The electrons have a spin, the protons in the nucleus have a spin. If you picture an electrically charged basketball, somebody's taken a basketball and rubbed it on their hair, and then they've, you know, it's one of the Harlem Globetrotters or something, and they've got the basketball spinning around on you. Well, once again, you've got electric charge circulating around, and that's current, and that produces a magnetic field. So any kind of an atom creates magnetic fields within itself. Some atoms are symmetrical enough that the atom as a whole doesn't add up to anything. For every electron that's going around in the one direction, there's an electron on a similar orbit going around in the opposite direction. For every proton that's spin up, there's another proton that's spin down. And they, when you add it all up, it balances out. Other atoms are not quite that balanced. Aluminum, for example. Each aluminum atom does have a little bit of a net magnetic field. But there's a lot of aluminum atoms in that chalk tray there. It's a big number. And they're all just arranged in a random way. One atom produces a field that points in that direction, and the next one's field points that way, and this one over here is that way, and maybe this one down here. And if I just, you know, spent the rest of the afternoon drawing atoms in random directions, well, you know, for everything that points in one direction, not too far away is another atom whose field's in the other direction. Still doesn't add up to anything. There are a few unusual materials, about half a dozen chemical elements, where you can get these organized. Iron is probably the most famous for that. Nickel is another one that's not too far behind. Actually, I used to keep some Canadian money in my drawer here. I don't feel like looking for it right now, but you get an American dime and you get a Canadian dime sitting next to each other. You come along with a magnet. The American dime just lays there on the table because it's mostly copper, and the Canadian dime leaps off the table. It turns out that the Canadians changed the composition of their coins about 20 years ago. I forget the exact date, but you get an old one, you know, 1985 or something, and it's mostly nickel. The new ones are mostly steel, and it makes no difference. They leap off the table in a magnet the same way, because nickel is ferromagnetic just like iron is. So what happens in a material like that is that it is possible, it doesn't always happen, because like a nail is not magnetized, not normally anyhow, but you can get them all lined up with each other so that it adds up to something, and that's what's going on in a permanent magnet. So where are the electric currents that create the magnetic fields from a permanent magnet? They are within the individual atoms, but it's whether it's the magnetic field coming from an electromagnet or whether it's the magnetic field from a permanent magnet, somewhere there is electric charge in motion, and that's what creates the field. So that's a somewhat longer version of what it says right there. Well, if we finish section 5, that's a good place to be. We're somewhat ahead of schedule. What's left of section 5 is that I want to run through example number 5 for you. And then number 6 is kind of similar, not exactly, but kind of. You work on that one. And when you're done with number 6, you can leave for the day. And I'll probably end up going over number 6 to an empty room like I sometimes do, but we want to get it in the recording here, you know. So anyhow, number 5 is pretty similar to, I believe it's the next lab. I can look right here in the drawer. Yeah, that's the one that's on top of the pile. So probably be doing, well, no, we won't be doing that on Monday. Monday's President's Day. So I guess we'll be doing it a week from today. Long weekend coming up, in case you hadn't. I think that's this week, isn't it? Yeah, you're agreeing with me. So. Yeah, right. Monday the 17th, President's Day. So what you've got in the next lab is, here it's just 2 wires, which creates, as you can see, a rather small force. What I did to make the, I kind of modified the original apparatus, but what's on there to make the force a little bigger is 2 bundles of wires, okay? If you've got a bundle of 5 wires, that'll create a magnetic field that's 5 times as strong as what you get from just 1 wire, all else being equal. But the one bundle of wires is mounted on a little balance, and then the other bundle of wires is right next to it. And it's really kind of similar to a triple beam balance, except instead of weighing something, you're measuring a magnetic field with it. But it's a balance with a counterweight on it, just like the counterweights you can slide around on a triple beam balance. And so you can measure the magnetic force between these 2 bundles of wires that way, and you compare that to what comes from a calculation very similar to this one. So you might want to be looking at this while you're doing the next lab. Anyhow, the basic idea is it's 2 steps. Question is, how much force does the one wire feel because of the other one? 2 steps. Step 1 is that the one wire creates a magnetic field around itself, whose strength is given by the formula a couple of inches further up the page there. Step 2, the other wire finds itself in that field, and you can calculate the force on that wire from the equation that we were using. Well, it's still written right here, actually, in problem number 4. ILB sine's 90 degrees, sine's equal to 1 in this case, because the field will be perpendicular to the wire. The field points through the page away from you. That, you know, if you imagine loops like I have up here, they come up out of the page, arch over the wire, go back through the page, pointing away from you down here where wire D is. So the field's in the Z direction, and the wire lies along the x-axis, and those are perpendicular, so the sine is equal to 1. So step 1, find B. Step 2, find F from B, and the details look like this. I guess I have to cover the direction also. It asks for that as well. So I named them wire C and wire D because A and B seemed like a bad idea because I'm using B for the magnetic field. So C produces a field. How strong and what direction is that field where wire D is located? For the strength of it, V equals 0I over 2 pi R. Mu again is a fundamental constant. You can look that up in some table in your reference handout. 4 pi times 10 to the negative 7. 10 amps. 10 amps is the current in wire C because we're finding the magnetic field produced by wire C. R is the distance from the center of the wire to the point where you want to know the field. Well, we want to know the field where the other wire is, and it's a centimeter away. So convert to meters, 0.01. Let me point something out that's not terribly important, but simplifies punching it up a little bit. This was more important in the old days before we had electronic calculators and you had to do stuff like this by hand. If you punch up 4 pi times 10 to the negative 7 times 10 divided by 2 pi, you'll get the right answer if you don't make any mistakes. But notice that pi over pi cancels out. And 4 divided by 2 is 2. It's kind of obvious and staring you in the face. You might as well simplify it down before. All you really have to punch in is 2 times 10 to the negative 7 times 10 divided by 0.01. And even if you're not doing the calculations by hand, it's nice to do that because the fewer keystrokes you make, the less likely it is you'll get one of them wrong and make a mistake. Anyhow, whether you do that or not, it should come out 0.0002 of a Tesla. For the direction of it, draw some pictures. There's the wire. And wire C has a current in it, flows toward the right. That's your thumb. Okay, again, there's the right-hand rule for this, and there's the right-hand rule for that, and there's the right-hand rule for the other thing. And the right-hand rule for what we're doing right now is that you grab the wire with your thumb pointing in the direction of the current. Your fingers wrap around that wire pointing in the direction of the magnetic field. So that would be up the back, sticking out toward you up here above the wire. So there's a few little dots to be the magnetic field up there. The field lines arch over the wire and go back down into the page. If I was over here looking at this so the wire comes right straight toward me, I'd see the field lines circling around the wire in this angle. Seen from the side here, they kind of go like that, okay? Well, we're interested in the field down here because that's where the other wire is. So at the location of wire D, the field has this strength and this direction. Not the answer yet. That's just halfway. Got my wires all tangled up on the camera here. to the force on wire D from that field. Probably best to keep the magnitude and direction as two separate questions. So for the moment, I just want to calculate a positive number for how many newtons. I'll get to the direction in a moment. That's why the absolute value signs. Oh, that's, I'm looking at the wrong thing. That's the example I'm going to have you do. That's number 6. You know what I'm going to do? I'm going to fold the page in half here so I can't accidentally look at the wrong one. This is the difference between the example that I am supposed to be doing and the one that you're going to do in a minute. Is the first half of it is exactly the same as this. But then when you get to the second half, instead of it being the force on a wire, it's the force on an electron. So you got a particle moving through empty space. Force on a particle in empty space is given by this. But I'm supposed to be doing number 5, the force on a wire is that. So now we're looking, this is the force, probably should have written that down. The force from that field, force acting on wire D. Wire D has a current of 7 amps in it. And it says each one is 1 meter long. Put that in for L. For the strength of the field, that's the number I calculated earlier, 0.0002 of a Tesla. And as I said a couple of minutes ago, the angle is 90 degrees. .0014 of a Newton. So that's half the answer. That's the magnitude of the force. That's how hard the wire gets pushed. For the direction, let me try one of my 3-dimensional drawings again here. So the blackboard is the XY plane. The Z-axis sticks out toward you. And I've determined that the magnetic field points in the negative Z direction. So something like that. And the current is flowing along the x-axis toward the left. Kind of like that. So get your right hand out. The field is the direct where you line up your fingers with the field. And just like all those examples I had you do earlier, the direction that positive charge is moving, the velocity of the charges or the current, whatever you want to call that direction, that's your thumb. So I'll get my hand in there and do that. And fingers are pointing through the blackboard in the direction of the magnetic field. My thumb points to the left because the current goes to the left. Looks like my palm pushes the wire downward. So magnitude is, let's extend this a little bit. Magnitude is 0.0014 of a Newton. The direction minus y, in other words, it's repelled by the other wire. It's pushed directly away from it. If the question also asked for the force on the top wire, it doesn't, but if it did, it would be a very quick follow-up thing. Easiest way to look at it is just to say Newton's third law. If C pushes on D, D pushes back on C with an equal and opposite force. It would be 0.0014 in the plus Y direction. So they repel each other. If the directions of the wires, if the direction of the currents had been the same as each other instead of opposite, then it would have been an attractive force rather than repulsive. So anyhow, your job now is to kind of imitate what I just did, except when you get to this point here, you do what I almost did before I erased it and realized I was looking at the wrong problem. Number 5. No, number 6. Starts out a lot like number 5. So first step, once again, is to find the magnetic field coming from the wire. The only thing that's, well, the numbers are a little different is all. Where I had 10 amps before, now it's 6.5 amps. And the distance this time is 0.025 of a meter. 2.5 centimeters from the wire to where the electron's located. So you punch up those numbers and it should come out 5.20 times 10 to the negative fifth of a Tesla. The direction is exactly the same thing as it was in the previous example. You've got a wire that's carrying a current toward the right. So down here below that wire, the magnetic field points away from you. Up here above the wire, it points toward you, but we don't care about that because the electron's down here. So the second step is to find the force on an electron due to being in that magnetic field. Oh, your quiz is right here. Okay.
Thank you very much. Have a nice day.
You too.
Have a nice week, actually.
Yeah, actually, yeah. So as I started to write before, let's see, you're all set? The magnitude of the force, first of all. Since I'm only calculating a positive number of newtons, that's why I ignore the minus sign on the charge of the electron. Charge of an electron is something you can look up in your formula sheet. 1.6, just slightly over 1.6 times 10 to the negative 19 coulombs. That's the speed for the electron given in the question. That's the strength of the magnetic field in Teslas that I calculated a couple of minutes ago. Theta is 90 degrees. Theta is the angle between the direction the electron is going and the direction of the magnetic field. The field is in the negative z direction. The velocity vector is in the negative x direction. X is perpendicular to z. You managed to push all the right buttons. That comes out 2.5 times 10 to the negative 17 Newton. As for the direction, well, maybe I don't really need to draw the picture over again because I still got it. Oh, the cords are caught. There we go. Back here from the previous question. It's kind of the same picture all over again. Not sure how the camera ended up lower like that. Okay. So this time, instead of I for current, maybe V for velocity. That's the direction that the electron is moving. Just like in the earlier example, the field points in the negative z direction, so you get your right hand in there, and once again, the palm pushes down. Well, in number 5, that made the answer negative y, but this time we're dealing with a negative particle. So anytime it's a negative charge, that reverses the direction, which makes the answer positive y. And that concludes another highly entertaining physics class.